All right, so we looked at limits, like what is the limit as x approaches 2 and 0 and all kinds of things. So we're going to look at what happens at limits at infinity, which we did talk about a little bit when I first gave you limits. But this is tied to end behavior. So we don't really care about the middle, what's happening at 2. We care about what's happening at the ends, which will be positive and negative infinity. Okay, so the end behavior of functions can be discussed in terms of limits at infinity. Recognizing the end behavior patterns of power, polynomial, and rational functions can help identify limits at infinity. So we're going to use what we know about functions that we've already learned and know what to do with. So if we look at power functions, so remember power functions just had one term. It was just like if I had x to the 5th, I wouldn't also have plus x to the 4th plus x to the 3rd. Like x to the 5th, that would just be it. And we know what their end behavior looks like. And we did it when especially when we were doing polynomials, just like kind of is it up, down, whatever. If n is even, so if it's positive, then we know that it's up, and that's how we talked about it, right? If it's odd, then it would be down, up. And if the term was negative, then it would just be reflected in the x-axis, right? Remember all that? Knocking off the cobwebs. So the way we write these limits, we would say the limit as x approaches negative infinity of f of x equals, so it's just f of x is x to the nth where n is even. So since it's up, as x approaches negative infinity, f of x is approaching infinity, right? We just were writing it before as x approaches negative infinity, f of x approaches infinity, right? So it's the same thing, just different notation at this point. All right, so then we will say the limit as x approaches infinity of f of x is equal to, well, as x goes to infinity, this is infinity. We can just tell by our little arrows that we did. If n is odd, then when I say the limit as x approaches negative infinity of f of x, what's that going to equal? Negative infinity. And then the limit as x approaches infinity of f of x equals what? Infinity. Okay. Easy enough? Those are your power functions. Okay, so now let's look at the polynomial functions. Polynomial functions, alrighty, so let p be the polynomial function. So these look, long and crazy, but that's because it could be, 3x to the 5th plus 2x squared plus whatever. We could have an infinite amount of terms, so the generic one has to look all yucky. But instead of having to deal with the entire polynomial that could be an infinite number of terms long, when you're looking for the limit of this, however many terms there are, so the limit as x approaches negative infinity of p of x is going to be the limit as x approaches negative infinity of a sub n times x to the nth. And what that means is we only care about the leading term. No matter what other mess is in there, it's irrelevant. Right, so then when we do the same kind of thing happens here. The limit as x approaches infinity of, instead of the entire thing, I only have to do a sub n times x to the nth. So it goes on to say this means that the end behavior of a polynomial can be described as the end behavior of its leading or highest degree term. So the leading term is the one with the highest degree. It's not always the one that's first. If it's written in the proper order, which, there's a way that's proper, but it's not wrong if you don't, where the exponents are from greatest to least, then it is the first one, but that's not going to happen every single time. If you're watching the video, I'm going to be interrupted a ton today, so if it starts and stops and my words don't flow, I'm sorry. I forget what I say when I hit pause. All right, so this says to evaluate each limit and use the properties of limits when necessary. So this is going to be equal to the limit as x approaches negative infinity of x to the 4th, because I only care about the leading term, okay? So then if I do direct substitution, negative infinity, when I substitute it in there to the 4th power, what's any negative to the 4th power? Positive. Or we can look at it as just the end behavior. It's even and it's positive, so it's going to look like this, right? And since it's up, up, the answer has to be infinity also. Okay, easy enough. Oh, there's some. All right, on number 2, what's my leading term? X to the third, and that negative goes along with it, all right? So this is going to be equal to the limit as x approaches infinity of negative x cubed. So x cubed would be down up, but it's negative, so this is my end behavior, right? So as x approaches infinity, what's my answer? Negative infinity. Make sense? Because we're talking end behavior. We don't care about what happens in the middle, because all that other stuff means that, remember when we did polynomials and we had to see if there was a bounce or a wiggle or whatever, and there was all kinds of stuff going on in the middle. We don't know what's going on with these, and we're not interested. We're just interested in about the end behavior. What's your question? Yes. We reflect it, and it's up, down. Exactly. All right, number 3, what's my leading term? Negative 8 to the 6. So this is equal to the limit as x approaches, why do I keep doing that? I'm sorry, it goes underneath it. I'm doing it wrong. As x approaches negative infinity of negative 8x to the 6th. All right, so it's even, so it'd be up, up, but since it's a negative 8, my end behavior is down, down. So my answer is negative infinity. So I'm going to show you another way on here because I think it's one of the ways that Delta Math shows you, and it's also an acceptable way to do it. It's just not really necessary for us at this point. So we're going to do a little or. We can say it equals negative 8 times the limit of x, as x approaches negative infinity, negative infinity, of x to the 6th. So you can basically like factor out that negative 8. Okay, does that make sense? And since this, if I'm looking just at x to the 6th, that's up, up, right? Which means from this, my answer would be a positive infinity. Positive infinity multiplied by 8 is still infinity, and then the negative makes it negative infinity. So if you see something out in front of the limit, it's just basically factored out. You'd get the same answer either way. There's really no reason not to just do it like this right now. Okay? Yeah, you just ignore that. Because infinity, even infinity to the 6th is still infinity. If I multiply by 8 or whatever, it's still just infinity, because infinity is a wacky kind of topic there. All right, you do number 4. I'll give you a minute to do that. Any questions? We're all good? All right, let's talk about reciprocal functions. So reciprocal functions are part of the rational function family. What makes a function a rational function is that it has variables in the denominator. What makes it a reciprocal and not just a regular old rational is that the variables are only in the denominator. We don't have any in the numerator, okay? So these are 2 parent functions that we looked at early on. If I just have 1 over x, looks like this, okay? And what's going on here at y equals 0? An asymptote. If this is 1 over x to the nth, where n is a positive integer, it looks like this. But we also need to write, not only is it a positive integer, it has to be an even positive integer. If it's odd, it's going to look like this also. So for this one, the limit as x approaches negative infinity, what does f of x approach? 0. And then the limit as x approaches infinity would be what? 0, right? Because it's in behavior. I don't care what's happening right here. But as x gets bigger and bigger and bigger, when you have a horizontal asymptote, it stops at least one side from going to infinity, okay? And then, so they're both 0. This one just approaches it from the bottom. This one approaches it from the top, okay? And then if I have this, where it's an even positive integer, the limit as x approaches negative infinity is what? 0. And as we approach positive infinity, 0. And they're just both approaching it from the top. Okay. Everybody okay with that? All right, so let's look at what this looks like. What we're going to do here is we're going to use direct substitution. And since I'm substituting in, I don't rewrite the limit. Like once you start substituting stuff in or evaluating, you stop writing the limit part. So this is the limit as x approaches infinity. So I'm going to substitute infinity for x. So I get 1 over infinity to the 4th minus 7. Okay. Now I can't get a real number from that because infinity is not a number. But we're talking limits. What is it approaching? And if so, infinity to the 4th is just infinity. 1 over infinity, so in a fraction, if my denominator is getting infinitely bigger, what's happening to the fraction? It's getting infinitely smaller, right? And if it's getting as small as it possibly can, that means it's getting closer and closer to what? 0. So what this really gives me when it's a limit is 0 minus 7, which is negative 7. So let's think about this from a function perspective. 1 over x to the 4th, ignore that negative 7 for a minute, falls into this category, right? I'd have a horizontal asymptote at 0. But then this 7 means I have a vertical shift down 7, so my asymptote shifts down to negative 7, and that's why that's my limit. Okay, does that make sense? Okay. So then let's look at, oh, I'm missing a fraction bar again. Let's substitute it in here. The limit as x approaches negative infinity, so I'm going to have 5 over negative infinity squared plus 1 over negative infinity. Okay, so negative infinity squared is a positive infinity. 5 over positive infinity would approach what? 5 over infinity. What did 1 over infinity approach? 0. So 5 over infinity is also going to approach 0, right? Because eventually it's just, it's going to get infinitely smaller. 1 over negative infinity, that's also approaching 0. It's just approaching it from underneath. So my answer here is 0. Okay. Questions about that? Well, if infinity is on the bottom, it approaches 0. If infinity is on the top, it approaches infinity. Does that make sense? Because infinity divided by 2 is infinity. Infinity divided by 1,000,000 is still infinity. Infinities can make your brain hurt sometimes when you really get into all that stuff. Okay, so let's talk about a generic rational function, meaning I have variables in the numerator and denominator. So if I do that, then let's say we substituted it in here. I'd have infinity squared over infinity cubed. Well, is infinity squared bigger than infinity cubed? No, they're the same because it's infinity, right? So you can't really do direct substitution if you have variables in both. So instead, what we do is by dividing both the numerator and denominator by the highest power of x that appears in the denominator, we can use all those rules that we have. Okay, so this is going to seem odd at first. It's going to look a little weird, but you're not going to have to do any crazy fraction stuff. It just kind of seems that way at first. So the highest exponent, the highest power of x in the denominator is x cubed, right? So I'm going to divide every single term by x cubed. So this is going to give me the limit as x approaches negative infinity. That does say negative infinity, right? It's kind of just the blob up here. So, so this is going to give me 6x squared over x cubed plus 2x over x cubed. The denominator is 2x cubed over x cubed plus 3 over x cubed. Okay? We all good with that? So then we are going to simplify that sum. This is going to give me the limit as x approaches negative infinity of, so 6x squared over x cubed is going to give me 6 over x plus 2x over x cubed is going to give me 2 over x squared. Then 2x cubed over x cubed is just 2 plus 3 over x cubed. Okay, everybody with me? Good news is we don't have to get common denominators. Totally don't need to. We can evaluate now. If I substitute in negative infinity, 6 over negative infinity, since it's in the denominator, it approaches 0. Plus 2 over negative infinity squared also approaches 0. Spin. In the denominator, I have 2 plus 3 over x cubed will give me what? 0. So this becomes 0 over 2, which is just 0. We good? All right. So let's look at another one. What am I going to divide by on this one? X squared. Good. So this is going to give me the limit as x approaches infinity of, and I'll have 5x to the 4th over x squared, and then x squared over x squared plus 2 over x squared. So then I'm going to clean it up, and I'll get the limit as x approaches infinity of, so in the numerator, I will get 5x squared. In the denominator, I will get 1 plus 2 over x squared. Okay. So that's my limit with all the x's still in there. Then I'm going to evaluate, so I'm going to substitute in that infinity. So 5 times infinity squared, what's that going to give me? Infinity, right? And then I'm going to have 1 plus, what is this approach? 0. So that gives me infinity over 1, which is infinity. Everybody good? Any questions? All right, what am I going to divide by in number 11? X. So I'm going to have the limit as x approaches infinity of 2x over x minus 7 over x, and then 8x over x plus 1 over x. Then I'll clean that up. Limit as x approaches infinity of 2 minus 7 over x, and then 8 plus 1 over x. Everybody with me? Now I'm going to take that infinity and substitute it in. Well, 2 is just 2. And then 7 over infinity would be 0. And then I have 8 plus what? 0, which is 2 over 8, which is 1/4. Any questions at this point? All right. So that's the algebraic way to do it. Let's think about what we know about rationals already. Our rationals could have horizontal asymptotes, but they didn't always, because they could have slant asymptotes, right? We have to look at a rational function and decide what my asymptote was. We look to see if it was top heavy, bottom heavy, or tied in degree, right? So if I look at number 9 and I look at these, is this top heavy or bottom heavy? Bottom heavy. So this one is bottom heavy. And if it was a bottom heavy function, we always had an asymptote at y equals 0, right? That's why our limit is 0. This one is top heavy, right? Top heavy meant no horizontal asymptote, possible slant asymptote, right? So if I don't have a horizontal asymptote, there's nothing to stop me from going to positive or negative infinity. That's why my answer is infinity. Okay? This one is tied in degree. When it was tied in degree, we had a horizontal asymptote. It was at the y equals the ratio of the leading coefficients, 2 over 8. That's where the 1/4 comes from. Okay? So this is the algebraic way to do it. Something you need to see. You need to be taken through this so you understand why it's happening and what you can do algebraically, especially if it's not something that you can recognize. But because we do know things about rationals, we can use that information and not have to always do all this work. Okay? There's going to be a lot of things where you're shown why it works and what happens, and then since we understand other things, we can make it a little easier. So let's see how we can make that a little easier. So it says, looking at the examples above, notice that the limits of rational functions at infinity follow their horizontal asymptotes. We can generalize limits of rational functions at infinity using this principle. So, if I have p of x over q of x, if the degree of p is less than q, so if p is less than q, that means that it is bottom heavy. And we know if it's bottom heavy, we have an asymptote at y equals 0. That means the limit is 0. It's not y equals 0 because that's a line. That's the asymptote. Okay? If the degree of P is greater than Q, that means that it is top-heavy. And if it is top-heavy, I don't have a horizontal asymptote, so there's nothing to stop it from going to positive or negative infinity, depending on the problem that you're on. Okay. If they're equal, that means that they are tied in degree. And the limit is the ratio of leading coefficients. Okay, make sense? Just follows right along with what we did with rationals. So you notice that that information is not going away either. So when I look at this, all I have to look at is this right here. That means that this is the limit as x approaches infinity of 2x over x to the fourth. And I don't have to do any of that division stuff. This one is bottom heavy. So what's my limit? 0. Okay, we good? All right. Then this one is going to be the limit as x approaches negative infinity. I'll look at these two. It'll be of 10x cubed over negative 2x cubed. That's tied in degree. So what's my answer? Negative 5. Any questions about those? All right, so then this one is going to be equal to the limit as x approaches infinity of negative, that negative sign's important, and then I just circled it, now I can't even read it, x cubed over 2x squared. X cubed over 2x squared. That one's top heavy, which means it either goes to positive or negative infinity. So you basically have to substitute in your infinities again, all right? So this negative sign's important here, right? And then I'd have negative infinity, I'd have positive infinity cubed is going to be positive, right? And then this would be positive. So since this is positive over positive, it's just infinity. So it's negative infinity. Had this been negative infinity right here, let's just talk about what that would look like. If this was negative infinity, I'd have this negative sign. Negative infinity cubed is negative infinity, right? Over negative infinity squared, which is positive infinity. So I'd have had a negative, negative, positive, which would have made this positive. So watch your signs on that one. That's one on the shortcuts where it's the only one you really have to kind of think about as you do it. Okay. Any questions? We good? All right.